teach myself some of these basic topics in other fields. So I'll first start with the background just to get us all on the same page, and it'll kind of help me introduce the story as to why I'm even here. And then we'll get into the experimental results and discussion for what we saw in the lab, what I saw in the lab. And now, once we see both of those, I'll show you how the properties that we got are disappointing compared with the great properties that have been reported for individual nanotubes. And that will lead the discussion into investigating those strength limiting factors and analyzing their effect on the yarn strength, as well as possible solutions and future potential after that new insight. And then we'll briefly touch on the sensing application, because that, as you can see from the title, was initially the main goal of this research. And so we'll wrap up with that. So carbon nanotubes were discovered in the early 90s. Multi-wall were first, and then single wall. Single wall can be in 1.36 nanometers is roughly the lowest that I've seen, but it's not uncommon to see multi-walls that have 40 or more walls. It depends on growth parameters. And initially they're appealing because they're high aspect ratio, small diameter, incredibly long length. So in a load transferring system like a yarn, you have a lot of frictional surface area to work with. And initially there were a lot of researchers that looked into carbon nanotube strength, or many properties, and some of them are summarized here. You can see 1800 gigapascals as compared to carbon fiber pan and pitch, and 150 gigapascal strength. So right off the bat, that looks incredible. And the conductivity is almost double what copper is for if you have a single wall nanotube. And the gauge factor is 500 times more than foil strand gauges. So all these properties are incredibly appealing. But to make individual nanotubes is not very practical, so the carbon vapor deposition method is used to make millions or billions of nanotubes grown like a forest on the substrate, and the left picture on the bottom here. And depending on the growth parameters, you can get really fine, nice quality, super aligned arrays. And furthermore, depending on the growth parameters, you get what we call a drawable CNT array, where you can, in figure A, I'm sorry, Dr. Mesley, I just realized I'm not telling you when to change the slides. Are you keeping up? Is he gone? In figure A, you can see that if you just grab a small part of the array with a razor blade or tweezers or what have you, you can draw it out. It acts a lot like spider web. It almost sticks to everything. But you can then, in figure C, you can see that you can insert twist and you get a resulting yarn. And then the two yarns on the left side are there to show that the quality of the yarn depends on the quality of the array and how you spin it, and maybe even post-processing techniques that other research groups have looked into. And then what I'd like to show quickly is a video that was published by Dr. Ray Bachman's group out of UC Dallas, showing a ribbon being drawn from an array. So to the far right off the screen, the twist would be inserted. So this is a side view. And you can see bundles here that peel off, and then as they peel towards the bottom, they'll peel the next iteration off. This is a good one that's coming up here, because that'll peel this next bundle away. And that self-assembly is how the continuous drawing process is to some degree thought to work. It's still a focus of research. So let's get into the mechanical properties for what we saw in the lab. I first need to talk quickly about the experimental procedure. So in order to get a yarn with a certain twist angle that we like, we use a textile equation, tan alpha equals pi dt, where alpha is the surface twist angle, d is the diameter of the resulting yarn, and t is the twist factor. So twist factor is where we really control it in the laboratory. The twist speed, if you look at the bottom image, the spindle, we can control its rotational speed in increments of 1,000 RPM, and then the linear track and carriage can draw the spindle backwards using just a basic motor and power supply. So we plug in this to get a prescribed twist angle that we'd like. Then we take the yarn and lay it across a tab paper. And for now, just ignore the copper wires. We'll look at that a little bit later. This procedure follows closely with an ASTM standard for testing textile yarns. You attach the yarn to the gauge paper at the edges of the square cutout to fix its boundary conditions. Load this all into the clamps of the tensile tester. Cut those side strips off, and now the yarn is ready to take the load from the tensile tester. This is a representative curve. This is one of the top end representative curves. And two things I want to point out. One is the shape of this curve.